This video is going to show you how you can use the UART protocol to output from your Android Things application. We'll discuss the Raspberry Pi Rainbow Hat and its actuators. In this case, the Rainbow Hat doesn't have any UART components, but it does have breakout pins for UART. We will use these to attach a ZX sensor and detect some cool hand gestures, Minority Report style. We'll use gesture sensors to change our Rainbow Hat LEDs through a range of colors. Let's get started. UART stands for Universal Asynchronous Receive and Transmit. UART can also be called a serial port, which you might have heard of. UART can work with 3 or 5 pins on your board and uses one pin to transmit data and another pin to receive data. In the 3-pin configuration, they are transmit, receive, and ground. In 5-pin configuration, there are an additional 2 pins for request to send and clear to send, which act a bit like traffic lights for the data pins. Our peripheral has a 3-pin configuration, but don't worry, Android Things abstracts most of this detail away for you. The gesture sensor comes as a separate board from the Rainbow Hat, so you have to solder a connector to it before it can be wired up. As a brief guide to this, first cut a strip of female headers down to a length of 9 pins. Then solder this header onto the ZX board. You can now plug the sensor board to the Rainbow Hat with 3 male-to-male jumper wires. Here is how they connect on the top of the Rainbow Hat. And here is how they connect to the ZX gesture sensor board. Our Raspberry Pi is now plugged in and connected via ADB ready for development. We have the Rainbow Hat connected to the top of our Raspberry Pi, and we have the ZX sensor wired into the UART pins of the Rainbow Hat. We're going to code our app so that when we make a swipe gesture over the ZX sensor, the LEDs on the Rainbow Hat change color. To understand how this peripheral works and determine the protocol needed to talk to it, we should consult the ZX sensor documentation and, if needed, the datasheet. In the documentation shown here, we can see the ZX sensor being described in terms of its hardware components and usage. Then here, it says we can use UART or I2C to drive this sensor. UART is the communication protocol for sending and receiving packets of bytes. However, what is contained in those bytes is proprietary to the sensor. To understand the format of this information, we will have to refer back to the datasheet. Okay, let's program the gesture sensor. Here I have an Android Things project already set up in Android Studio. If you aren't sure how to get your project to this point, you can revisit the previous first app lesson for instructions. First, we create an instance of Peripheral Manager Service using this code. This is the Android Things SDK class that allows us to open connections to different board pins using the different available protocols. Using this instance, we want to open a UART connection. The open method takes one parameter. This is the name of the UART bus we want to use. The UART pins on the top of the Rainbow Hat are known as UART 0. When we open this connection, we are given back a UART bus variable that will now allow us to communicate using the Android Things SDK UART class. We'll use this variable in multiple Android activity lifecycle methods, that's why we make it a field. Notice that we have to wrap the open UART device call in a try-catch block. This is because the method, and most other methods we will use in the future, all throw a potential IO exception. This is due to the fact that we are dealing with hardware and at any moment the pin or the peripheral could become unavailable, for instance because of a loose wire. At that point, calling the method would throw this exception. We are assuming all our wires are nicely connected, and if we do get one of these IO exceptions, it would be really bad for our app, and actually, we want to crash straight away, so we can diagnose the problem as soon as it happens. That's why in the catch block we throw an illegal state exception, as we are not expecting nor wanting this to happen. This is known as failing fast and is a clean code best practice. The benefit of this is our bus variable is either a fully instantiated field at this point, or our app has crashed. Therefore, from this point on, there is no need to check if our bus field is null. It never is. Opening a connection to a pin is capturing this pin as your resource, and like with all resource management, it is good practice to release resources once you have finished with them. Also, if we have an open connection to a pin, no other code can open a connection to that same pin until we close our connection. Since we open the connection to our pin in the onCreate method, we should use the symmetrically matching pair from the Android lifecycle to close this connection. Therefore, we close the UART bus connection in onDestroy using this code. Again, close can throw an IO exception. We can't do anything about this if we get an exception, but we can log it out so that we know for next time our app starts if something unexpected had happened in the past. To speed things up, I have already read the ZX sensor datasheet for us. Whenever we configure a UART bus, we need to set the baud rate, data size, parity, and stop bits. Baud is the speed of communication. Data size is how many bits are expected at once. Parity is a way to ensure the integrity of the data, and stop bits can be used for time interval between transmissions. From the datasheet, we can see the baud rate is 115,200, the data bits are 8, and there is no parity and no stop bits. The UART API has a callback called UART Device Callback. This callback is invoked when there is data available to read. Let's register our interest in listening to data from the ZX sensor with this code. We are registering in onStart So as a best practice, remember to unregister in the symmetrically matching method, in our case onStop, with this code. Once we have registered, we can read data from the device inside the onUART device data available method. The datasheet explains to us that we will be sent a message code of 1 byte, followed by a data payload. The data payload has a maximum size of 2 bytes. Therefore, we can read the UART's device buffer with this code, making sure our buffer has a maximum size of 3 bytes. We want to detect swipe left and swipe right gestures, so let's see what they look like in the datasheet. The datasheet shows us that any data we receive with the message code 0xFC will be a gesture event. Then, when we receive the 0xFC message code, the payload will be 0x1 for a swipe right or 0x2 for a swipe left, followed by another byte for the speed of the swipe. Let's code that up. Handling the gesture event, message type is the first byte of our buffer. We return early if the message type is not the one we expect for a gesture event. Next, we check the gesture code, which is the second byte of our buffer. If this is 01 or 02, then we know it's a swipe right or swipe left. Let's give ourselves some visual feedback when a gesture event happens. Here I have created a class called LED-strip that will turn the LEDs on and off. If you're interested in the details, see the SPI lesson. We set up this LED-strip in the onCreate and tear it down in the onDestroy. Now, when we get a swipe right, we will tell the LED-strip to change to the next color, and if we get a swipe left, we will go back to the previous color. Let's run our app and perform some gestures. Then we can see the UART protocol working as the LEDs change color. That's it. You now understand how the Android Things UART communication with peripherals works. You can interface with a gesture sensor, reading its buffers and identifying gestures. You also understand datasheets to configure UART devices. This knowledge transfers to reading other datasheets and coding other UART peripherals, such as printers, GPS devices, or LCD displays.